Welcome to this Econ 2300 Exam 1 review. Let's go ahead and jump right in. The first example that we'll be working with uses a probability mass function. So I like to play the game Settlers of Catan, and in the game you roll two six-sided dice. And what you roll determines, well, not just what you roll, but where you place your settlements, and what you roll determines how many resources you collect throughout the game. So let's consider a table really quickly here. So we're going to be rolling two six-sided dice, and let's draw a table here in which we have the observation value. In other words, the number that we could roll with our two six-sided dice, and the probability, f of x, of rolling that particular number. Okay, and so the outcomes, obviously you can't roll a 0 or a 1, because at the lowest, you roll two six-sided dice, you're going to roll 1 and 1, which is 2. So we can roll a minimum of 2, rather. We can roll a 3, 4, 5, 6, and so on, all the way to 12, right? Because we've got a 6 on both of the dice. If we rolled two sixes, that's 12. Can't roll anything more than 12. So the probability of rolling anything other than what we've got here is 0. Now, it's important in this case to understand how many total possible combinations there are as a result of rolling these two six-sided dice. So how many total possible different ways could the dice be rolled? We have to consider that there are two dice, each with 6 sides. So we can use the counting rule here, in which we have, let's say, N1, which is the number of outcomes that are possible with our first event. That's the first die that we're rolling. And the second, or multiplied by the second. And this will give us our total sample space. And we can do this because the two die that we're rolling are independent of one another. In other words, when I roll a 3 on the first die, that's not going to impact the outcome of the second die. Okay, we're assuming that these two dice are both essentially, perfectly made so that there's an equal 1/6 probability of rolling any of these particular outcomes on a single die. And also we're going to assume that they're independent, so the dice aren't bumping into each other or anything like that. Okay, so in this case we've got 6 possible outcomes, 1 through 6 for the first die, times 6 possible outcomes for the second die, and that gives us a total of 36 possible ways that these dice can be rolled. All right, so in this case, it becomes clear when you can create a sort of tree, probability tree for the first, and for the second, you can realize that there's only one possible way for us to roll a 2, and that's for each of these two dice to roll a 1. So in this case, this will be 1 out of 36. And I'll go ahead and give the rest to you. You can figure those out on your own. 2 out of 36, 3 out of 36, 4 out of 36, 5 out of 36, 6 out of 36, 5 out of 36, 4 out of 36, 3 out of 36, 2 out of 36, and 1 out of 36. Okay, so essentially we could write these all in decimal form, which I won't do for you here, but the first thing we want to ask ourselves is this. Is this probability mass function a valid probability mass function? And how do we determine whether this is valid or not? Well, a valid PMF will satisfy two conditions. Okay, the first is that the probability of any of these possible values that x could take on is greater than 0. And this is true for all x. So this is just a symbol for all x. So this is the first condition. The second condition is that if we were to sum together all of these values, all of these probabilities, so we could say sum up all of these different probabilities, then this will equal 1. Okay, and I guess sort of a third here would be a side note, and that is, for all other x's, not in this table, the probability of that x is equal to 0. Okay, which I explained that bit in the beginning. So now what is left here? Let's suppose we want to find what is the outcome that is most likely to occur. Well, you can kind of see that it's 7 here, but let's calculate the mean here. Okay, so we're going to find the expected value of x, which is equal to mu. Okay, which is also equal to the sum of all of our xi's times the corresponding probability. So in this case, we're multiplying to find the mean, expected value of x. We can take 2 and multiply that by 1 over 36. And we can add that to 3 times 2 over 36. And so on. Okay, so 4 times 3 over 36. And we can do this for all of these. And eventually, let me see, I'll erase that. Okay, and we get to the last term, that's 12 times 1 over 36. If we were to add all of these up, what we would find is the answer is 7. Which makes sense. And that 7 is the most likely outcome of rolling 2 perfectly balanced 6-sided dice. And if you play Settlers of Catan, you know that the reason this is the reason as to why when you roll 7, you get to move the robber. So, okay, so that is the first problem we want to review for this exam. Let's proceed. A few of the questions that you're going to run into are about telling the difference between quantitative variables, quantitative, and qualitative variables. So let's just do a quick review here. So quantitative variables are those variables that are a numeric measurement. Okay. And they're calculable, and they can be either discrete or continuous. All right, and qualitative variables are a description. And are categorical in nature. Okay, so, and I guess I should also explain the difference between discrete and continuous one more time. With discrete, you've essentially got a variable in which the possible values that this variable could take on are finite. or infinitely or countably infinite. Okay. Apologize for my handwriting there. It's actually a little bit harder to draw on this tablet than I thought. Okay. So what would be some examples of a discrete, let's say, discrete sample spaces? Also, one could be something like this, where possible values are 1, 2, or 3. Oops. Let's see here. Okay. So here you've only got 3 possible outcomes, and so the sample space is finite. Okay, another that is an example of countably infinite. This example would be something like the set of all integers. Okay, the set of all integers, looks something like this, and they include 0, 1, 2, 3, and so on. Now notice, you could continue counting all of these integers up, for an infinite amount of time. But the point is that this is what we call a countably infinite set. Okay, and any set that has a one-to-one relationship with the set of positive integers, or the set of integers here, is countably infinite. Okay, in other words, you can't take on values between 0 and 1, or between 1 and 2. Okay, and we'll continue on. We'll define continuous. Okay, continuous variables have an infinite number of possible values. And so basically anything between negative infinity and positive infinity. Okay, so examples could be, like you're measuring your, let's say, your income. You could make, 1,562,000 $721.43 or something like this. Maybe it's possible with certain currencies to even get into fractions of cents or something like that. Okay, and finally, let's just review the measurement scales. You may remember what they are. I'll list them out. There are 4: nominal, ordinal, interval, and ratio. Okay. Now keep in mind, nominal here, just a label only. Okay. Ordinal, yes, also has some, has a labeling property to it, so to speak, but it's also got an intrinsic order. Interval scale data has a label, it has order, but it's also got proportional intervals. And finally, ratio has all of that information from the previous 3, label, order, proportional intervals, but this time it's also got a real 0. Okay, whereas interval does not have a real 0. Not a real 0 with interval. Okay, it has an arbitrary 0. So using that information, let's go through a few examples. Okay. So the first example, maybe the number of marbles in a jar. Okay. Is this quantitative or qualitative? And if it's quantitative, is it discrete or is it continuous? And finally, what is the measurement scale that we would use to measure this variable? So obviously this is a quantitative variable, and it's also discrete, right? So we'll assume that none of the marbles are broken, so you can't have half of a marble or something like that. Or, a marble that's been, crushed into a million pieces or something like that. Now, is this ratio scale or is this interval scale? And think about that for a second. So if you said ratio, you're correct, okay? In other words, because there could be 0 marbles in the jar, right? In other words, 0 marbles in the jar here indicates that there are no marbles in the jar, right? It's the absence of a thing. So in this sense, we know we can describe this using a ratio measurement scale. Okay, finally, let's wrap that up. Let's do a few more examples. Let's say SAT scores. Okay, is this quantitative or qualitative? Okay, so this is quantitative, having probably taken the SAT yourself. Maybe you took the ACT, I'm not sure. But you know that you get a quantitative score, and this is a score that basically can take on incremental values, whole numbers, between 400 and 1600. So your score is essentially somewhere in here. 400 being the lowest, 410, 420, and so on. 1590, 1600 being the highest score for the current system. Okay, so this is quantitative. It's also discrete. And is this interval or ratio? If you said interval, then you are correct. Okay, why is it interval? Because in this case, there is no 0. The lowest score is 400. And even 400 being the lowest score, that's sort of an arbitrary cutoff that the test makers decided. Okay, 2 more examples. This one should be easy. The flavor of pizza. Okay, so flavor of pizza, is this quantitative or qualitative? Obviously, this is qualitative. And you have pepperoni, cheese, sausage, veggie, whatever. And what kind of measurement scale is this? This is nominal. Okay. Why? Because there's no intrinsic order here. This is just a label. And that's it. It describes the pizza. There's no calculations we can do on, pepperoni divided by sausage or something as ridiculous as that. Okay. And finally, last example. Let's assume we send out a survey and we use the Likert scale. Maybe this is the first time you've heard of the Likert scale, at least formally. But you've probably seen this if you filled out any sort of surveys. Usually they range from, how was your customer service experience? Was it very poor? Was it poor? Was it neutral? Neither good or bad, nor bad. Was it good or very good? Okay. This is an example of a Likert scale. So let's suppose we send out these surveys and we get a bunch of different responses about, our business's customer service or something like this. Is this quantitative or qualitative? This is qualitative. And what type of measurement scale are we using to measure this data? And if you said ordinal, you're correct. Why? Because not only are these labels, but there's also an intrinsic order here. Poor is better than very poor. Neutral is better than poor. Good is better than neutral. Very good is better than good. Okay. Now let's turn to an example about student heights. Let's say that we measure everyone's height in the class, and here we have the observations. And let's say we measure everybody who's 4'6", at least 4'6", to less than 5 feet tall exactly. Okay, so in other words, we've got a situation here where somebody's 4.5 feet tall, but they're less than, they are at least 4.5 feet tall, but they're less than 5 feet tall. And we'll throw out some other groupings here. Okay. From 5 foot to 5.5, from 5.5 to 6 foot, and from 6 feet tall to 6.5 feet tall. Okay, and we're just going to assume that elsewhere there are 0 people in the class that do not fall within this range. Okay, so we took everybody's measurements. We didn't find anybody that was 6.5 feet taller or less than 4.5 feet tall. So these are the observations, the categories, or the groupings, and then let's create a column for the frequencies. And a frequency here is just a count. So let's say that we found 2 people in the first category, 14, here I'll make my 2 better here, okay, 2, 14, 23, and 7. Okay. So with this example, I really want you to just know the difference between frequency, relative frequency, and percentages. Okay. Now let's create a column, and we'll call this the relative frequency column. So how do you find relative frequency? Relative frequency is calculated very simply as the count, or that is the frequency of this particular, of the observations you find in a particular group divided by the total. Okay, how many people do we have in total in the class? Well, if you add all of these up, 2 plus 14 plus 23 plus 7, you're going to get 46. So let's say we've got 46 students in the class. What is the relative frequency of those that are in this range, this first range, 4.5 feet tall to 5 feet? Okay. So some simple math here. I'll just go ahead and give you the answers. 0.043, 0.304, 0.5, and 0.152. Okay, and if you add all of these up, you should get either 1 or something very close to 1. In this case, you might get 0.9999 or something like that. Okay, and finally, let's create a column for the percentage. Well, this should be pretty easy. How do you find the percentage? That's just going to be the relative frequency multiplied by 100. 4.3% in this first category, 30.4%, 50%, and 15.2%. Okay, and of course, here at the end, you should get something very close to 100%. All right. In addition, you'll also need to know the different types of charts and graphs. Okay, charts and graphs. So I'll provide you a list of some graphs and some charts to review in the textbook. This list probably is not exhaustive, but you should be familiar with all of these different data visualizations and know how to interpret them. So I'll just include them here in a list. So bar charts, pie charts, dot plots, histograms, and also know Pareto diagrams or histograms. Know cumulative distributions. Let's see. You also need to know stem and leaf displays. Know cross tabulations. Know how to read a scatter diagram. Know how to read a trend line or just any line graph. Also be familiar with side by side and stacked bar graphs. Okay, so that should cover most of what you might find on this exam or future exams, but just know this list is not exhaustive. Okay, so you might find something on the exam that I haven't listed here, but you're certainly not going to run into anything that you haven't read in the textbook, okay, or that isn't there in the textbook. Also be familiar with all of the statistics symbols that we are using in this class. So I'll try to create a list of some of those that you'll see on this exam. We'll start with the parameter name. Oops. And then we've got two different cases. A case when we're dealing with an entire population. Okay, and this is the population symbol, population parameter symbol. And when we're dealing with just a sample of the population. Okay. So first, let's consider the number of cases, okay, or the total number here. And in this case, our total population size is capital N, and our total sample size is lowercase n. The mean for our population is the Greek letter mu, and for our sample, the mean is x bar. Let's do the standard deviation. For the population, this is sigma, Greek letter sigma, and for the sample, it's just lowercase s. For variance, this is sigma squared, and for the sample, it's just lowercase s squared. And for correlation, within our population, we'll be using the Greek letter rho, okay? And for our sample, just lowercase r. And one other symbol that you should be familiar with, that's level of significance. Okay, and this is denoted as alpha. Let's also be familiar with some formulas. Some formulas that you'll need to know the population mean, in this case, or rather let me create another little table here. So this will be for population, and this will be for a sample. Okay. So this will be the mean, the standard deviation, and the variance. So the first is calculated as the sum of all of our values divided by the total population size. Or in the case of the sample mean, this is the sum of all of our observations divided by the sample total. Okay. Or the number of observations in our sample. So let's do standard deviation. It's going to be the square root of the sum of each value minus the mean squared divided by our population size. And for a sample, it's more or less the same, just some different notation. Each observation minus the sample mean squared divided by n minus 1, this is lowercase n. And finally, for variance, we've got all of this, this here, we've got this squared. So basically it's the same thing, but without the square root sign, right? And more or less the same for our sample variance. But notice that for the sample standard deviation and the sample variance, we're dividing by n minus 1. Those are our degrees of freedom. All right, keep going here. We're about halfway through. You should also know how to calculate or how to find the median. And how do you find the median? Well, the first step would be to arrange all of your observations in numerical order. Okay. And the second step would be to count the number of observations. And the third step depends on whether you've got an odd number of observations or an even number. So if you've got an odd number of observations, then you can essentially divide the total count by 2 and round up. And whatever number you get to, that's the I guess, in numerical order there, that's the number that you would select. I'll explain through an example here. So let's suppose we've got an odd number of observations. So let's suppose we've got some observations here. And this is, let's say, 1, 3, 4, 6, 7, 9, and 10. Okay, so I've already put them in numerical order, and let's count to see how many we have. 1, 2, 3, 4, 5, 6, 7. Okay, so this is an odd number, so I can take 7 divided by 2, and I get 3.5, and I'll round up. Okay, and that becomes 4. There you go. So the median in this case is 6. This makes sense. It's right there in the middle. We've got 1, 2, 3 observations above it and 1, 2, 3 below. But if you've got a really, really large data set, then this strategy can help you. Okay, or if you're doing this in Excel, there's a function for it too that makes it quite easy. Okay, now if you're dealing with an even number, then it's a little bit trickier. So you're going to take the average of the two middle numbers. So let's do another example. Say this is our count and our observations. And in the observations, let's say we've got -1, 2, 7, 15, 23, 31, 40, 67, 99, and 108. Okay, so how many observations do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we've got an even number here. So we will just see that we can take these two in the middle, observations 5 and 6. So we got 1, 2, 3, 4, 1, 2, 3, 4 on either side, and we'll just take the average of these two observations. So 23 plus 31 divided by 2, and that's going to give us 27 in that case. Okay. You also need to know how to find the range, which is the maximum number minus the minimum number in your data set. And finally, quartiles. Okay. With quartiles, I'll just give you the definitions. Now that you know how to find the median, you can do this on your own. So for quartile 1, this is defined as the median of the bottom 50% of your data. In other words, 25% of observations fall below this, below Q1, and 75% fall above Q1. Q2 is just the median for all of your observations. Okay? You already know how to find median. Basically, 50% of the data falls below it, 50% of the data falls above it. And finally, Q3, which is the median of the top 50%. Okay, you guessed it. And in this case, we're saying approximately 25% of observations fall above this, approximately 75% of observations fall below this. Okay, let's continue on here. Let's review the empirical rule. Oops, let's see. Okay, the empirical rule is basically a rule that applies to normal distributions, or I should say data that is distributed according to a normal distribution, or perhaps you've seen this term, Gaussian distribution. And let's just draw a normal distribution here. This is not going to be perfect. I'm not a visual artist, but I'll do my best here. Okay, good enough. So we've got that nice bell-shaped curve, and right here in the middle, this is our mean. And we know with a normal distribution that this point here is the mean minus one standard deviation. This is the mean plus one standard deviation. We keep going out a further standard deviation. This is the mean plus 2 standard deviations. And we can go out a third one, the mean plus 3 standard deviations. And do the same out here. Okay. The empirical rule basically says this, that 34% of your data is going to fall to the left of the mean, between the mean and one standard deviation out. 34% of your data will fall here. 13.5% will fall here. 2.35% here, and 0.15% of your data there. Okay, it's the same over here. This is a nice, perfectly symmetrical bell-shaped distribution or normal distribution. And last, okay. And the important thing to note here is that within 2 standard deviations of the mean, so that's this point here, and that's also this point here, okay? In other words, you're going to have 95% of your data fall within 2 standard deviations of the mean. And that's the empirical rule. Now let's do a quick problem on joint probability. All right, so suppose that we're looking at a case where we've got a data set where we've got 1,200 CEOs. And these 1,200 CEOs, we've gathered basically some descriptive statistics here. Or some summary statistics rather. We've identified the number of men and the number of women. And we've also identified whether they are married or not married. Okay, so there we go. So do a little 2x2 matrix here. So this is joint probability. So 0.56 or 56% of those that were surveyed are men that are married. 0.03 are women who are married. 0.24 are men that are not married, and 0.17 are women that are not married. Okay. So now let's just find the totals here. Total men, total women, total married, and total not married. We'll need to use all of this. Okay. So how do we find this? Well, we already know that 56% are married men. So that's important for us to know. So 0.56 times our initial 1,200 plus, well, we also need the men that are not married. So 24.24 times 1,200. And this total, I'll go ahead and give it to you, is 672 plus 288 equals 960. Okay, so we've got a total of 960 men. Let's do the same for women. 0.03 times 1,200 plus 0.17 times 1,200. And this gives us 36 plus 204 equaling 240 women. How many of these CEOs that we've surveyed are married? Well, in this case, we know it's 672 plus our 36. We've already done the calculations. 672 plus 36 equals 708. And the total that are not married, that'll be 288 plus 204. So 288 plus 204 gives us 492. So you should be able to add this number and this number together and get 1,200. You should be able to add this number and this number together and get 1,200, and we do. So we've done everything correctly so far. Now, of men, what percent are married? And we could also ask, of women, what percentage are married? Well, this actually is a relatively simple question to answer now. We can take the number, let's take men first. Of men, what percent are married? We know 672 are married out of the 960. So this should be pretty easy to calculate. 672 divided by 960 times 100, and this gives us 70%. Now, in the case of women who are married, we know that 36 are married out of the 240. 36 divided by 240 times 100 equals 15%. Okay. And that should do it for a joint probability table. The last problem that we'll review for exam 1 is one in which we need to work with probabilities more directly. Okay, so we're about to get our hands dirty here. Let's say we're given a problem like the following. Of full-time KSU students, we're going to say that 26% work full-time. And of all full-time KSU students surveyed, 45% live on campus, and 18% both live on campus and work full-time. Okay? So they have a full-time job that they work and they live on campus. So let's run through a few of these. So let's define a few terms. Let's let event A be defined as students who work full-time. Okay, and let's let event B be those students that live on campus. Okay? All right, so the probability for a full-time KSU student to work full-time is 0.26. The probability of a full-time KSU student to live on campus is 0.45. And the probability of both living on campus and working full-time. Okay, so the probability of A intersection B is equal to 0.18. Remember that we use this intersection term basically to stand for and, right? And what does it describe? Let's use a Venn diagram here just to represent this. So suppose we've got a group of people in this circle, and this is A, and we've got a group of people in this circle, B. So these are the people that, the KSU students that work full-time, and right here in circle B, these are the students that live on campus. Okay, so by saying the probability of A intersection B, we are talking about this portion here that I'm sort of filling in with yellow, just the intersection of these two groups. So let's find a few things. Got all of our information here. So let's start by finding the probability that a student works full-time or that they live on campus. Okay, so the probability of A union B. And what are we describing graphically here? Using another Venn diagram. So we've got A and B. Well, we're essentially describing everybody in A and everybody in B. So essentially you're filling in, you're looking for everything in here because they can either work full-time, they can either live on campus, or they could be both. They could be in that intersection. Okay, so how do we find this? Well, you can see basically that what do we want here? We want the probability of A, everybody in A here, plus everybody in B. But we don't want to double count some people. What about those people that are in the intersection, right? So we have to subtract them out. Subtract out the probability of A intersection B. And this is actually equal to the probability of A union B. And we've actually already got this information. We know the probability of A is 0.26 plus the probability of B, which is 0.45. And we know this because it was given, 0.18. And altogether, this equals 0.53. Perfect. All right, now let's work through another problem. In this case, we will attempt to find the probability that a student is not working full-time and is not living on campus. Okay, so they're not working full-time and they're not living on campus. What are we trying to find here? We're trying to find the probability of A complement intersection B complement. Right? The probability, and I'll just read this again, the probability that they do not work full-time and that they do not live on campus. So to solve this problem, we need to use De Morgan's law. In this case, we'll be using De Morgan's law of union, which basically states that the probability of A union B complement. So in this case, what are we talking about here? We are talking about everything, let's say this is A and this is B. We are talking about everything outside of these two circles. This is equal to the probability of A complement intersection B complement, which is equal to 1 minus the probability of A union B. Okay. And if you'd like, I can link a proof for this, for De Morgan's law. It's actually quite easy to find if you just Google it. Okay, but we can essentially use this identity here to solve this problem. So let's go back. Okay, so I know that this is equal to, at the end of the day, the probability of A union B complement, which which is everything outside of those two circles, which is equal to 1 minus the probability of A union B. Okay. And this now is pretty easy because we just found the probability of A union B in part 1. So 1 minus 0.53 gives us 0.47. This is the probability that a student doesn't work full-time and doesn't live on campus. All right. Now we've got 2 more parts here, very quickly. Try to have this done in under an hour. Let's find the probability of B given A. Okay, given that someone is working full-time, what is the probability that they live on campus? And here, there's a nice formula that we can use to solve this as well. Okay, this I think flows from Bayesian statistics, here, Bayes' rule. And this is the probability of A intersection B divided by the probability of A. And here we already know what these are because they were given to us in the problem. So we've got 0.18 divided by 0.26. Feel free to verify that I'm using the correct formula there, and I'll calculate this for you. It's 0.69. So nice. All right. Last part. Last question. Are events A and B independent? Think about this for a moment. How do we know if if 2 events are independent? What's the way to prove this? Well, there's a simple test, really, and that is if the probability of A intersection B is equal to the probability of A times the probability of B, then A and B are independent. If not, then they are not independent. Okay? And think about this, logically for a second. Do you think that living on campus and working full-time are at all dependent? Well, yeah, I think that should be pretty obvious, right? That for many students, not all, but certainly for some students, they may choose to live on campus precisely because maybe their parents have covered all the bills, so they don't have to work. So clearly, there's some dependence there for some students. Okay, so let's test this out. We'll finish out. So what is the probability of A intersection B? That's 0.18. And is this equal to the probability of A times the probability of B? It's 0.26 times 0.45. Okay. And what is 0.26 times 0.45? That's going to be 0.12, okay? So we can see that these 2 events are not equal. So therefore, not independent. Okay. That finishes up the review for exam 1. Okay, best of luck to you on the exam.